today is going to be a quite different class from what was before, because I will tell you some things, but more importantly, what I would like to do is an exercise among all of us and to discuss the amazing diversity of welding and try to talk about welding in concrete. Before I start with the slides for today, I want to follow up on the exam. The exam seems to have gone pretty well. Some of you have asked what the average is, and I need to go check it out. I'm still in the learning stages with the exam system in E-class, and I followed up with a Socrates survey that I would ask you if you give me a hand and you fill it up. And if you give me a hand, that's actually giving a hand to yourselves, because I want to see what has worked so far, what you like, what we can do better. And many things maybe I can do better as we are learning all this new system of online classes and online exams. Some things about the exam I found exciting. For example, that you can watch a video and see and tell me what it is. That's something we couldn't have done if we had the exam on paper. So some things I find very exciting. Some other things are difficult, like it's all multiple choice. And I would have preferred to ask a problem with a little bit more of a development, but then it becomes much harder for you to submit answers. So please, if you go to socrates.com and you log into a room that is MatE 481-681, as I sent in the previous email, you do me a great favor. I'm gonna type it in the chat, so you know where to go if you wish to do it now. So you have to log in as a student, and the room is all right. So so far I got quite a few answers, and you seem to be very positive. So I'm very grateful, because preparing the class online has taken quite a bit of effort and a lot of uncertainty and anxiety, which I believe is shared with you. But I think we're doing okay. I think we'll be great. And by the time COVID is over, come to the lab and you'll be blown away. That said, let's start talking about welding procedures. So at some point, we need to tell the welder what electrodes to use, how to prepare the joint, how many volts, how many amps, all those things. This whole class is about that. But I want to give you a taste of what that is early on, and I'll give you the context of this. So, let's get them. So if you remember, we have discussed this in our class on terminology. We have the PQR, this is the procedure qualification record, and we have the WPS. And the WPS is much to a welder what the music sheet is to a musician, right? Here we have the notes, and we're saying at what time we play what note. And in the WPS, we say with what current, with what travel speed, with what electrode, those type of things. Before you're doing a weld of that carries some responsibility, we need to have this. If we're gonna be welding fences, we don't need to do that, right? Most of farm welding doesn't use this. But when you want to make a pressure vessel, when you're welding girders for a bridge, and when you're welding structures with responsibility, so you need to have it. So what does the WPS have? The WPS tells you the values of consumables, things, current voltage, travel speed, wire feed speed, joint preparation, the sequence in which you would weld, preheat, interpass temperatures. So here we have a very simple example that comes from the Lincoln booklet on gas metal arc welding, which you have uploaded with the notes on welding processes arc, right? And and you get to see, if you want to weld plate of certain thickness, they recommend these wire feed speeds, this current, this travel speed, this voltage. Something interesting about welding is that in welding, we don't try to do the best possible job. And that's so odd to hear, and it's so odd to say. And I myself feel that there is kind of something wrong about it, but there's nothing wrong about it. You don't do the best possible job. What you do is the job that meets the requirement. Now, if you could do something much better, then what you would do is something that is much cheaper, right? And if you think something much better is needed, then it's a conversation that needs to be had. For example, you can have a weld that has lots of spatter and looks super ugly. You know how to make a better weld. And you make the weld without any spatter. Now, if spatter was not a criterion for acceptance of the weld, for example, is a weld in a civil structure that will be covered with concrete, you gain nothing by reducing the spatter, and maybe you start to have a lower productivity in trying to avoid the spatter. So in the end, the weld that in theory was better because it had less spatter ended up being a worse weld because it met the requirement just as well as before, but now it became more expensive. So as we learn in this class, the idea is not to make welds that are better than the requirement. It's what they call fit for purpose. You meet the purpose, or you don't meet the purpose. But exceeding the purpose gives you no added value, no nothing. In this class, what we learn is not to exceed this purpose, but what we're learning is how to understand weld so we can meet the purpose at lower prices, or dealing with constraints. For example, if there is a lack of welders, or if we don't have one procedure, how can we deal with another procedure? And also, sometimes we need to weld things that are very difficult to weld because they crack, because many bad things can happen. How do you go about it? Then you need to think. So it's the definition of what is fit for purpose is sometimes when given by codes, sometimes given by client specs. Sometimes the client might say, I want you to follow this code, but in addition, I want these other particular things, right? And you meet those things or you don't meet those things. But I'm saying this for a millionth time, doing better than what is required buys us nothing. Being cheaper is awesome, but being better, if we were not asked, we shouldn't. Here you have an example of what a WPS looks like, right? This is a WPS that is done following ASME 9. That is something that we're going to be discussing in the last week of classes. It's the particular subtleties of codes, right? And here you would have the joint preparation, and you use the language of this code that says, okay, the P number, right? That means what base material you're using. You don't need to worry about memorizing this now, right? And what range of thicknesses you worry about, what filler metal you have. And this procedure actually has a second page. But I wanted to show you what it looks like. This you have here is a music sheet. It's the same thing. The only difference is that in this case, the music is coming together with molten metal. Here, you have another example. This is a blank that comes from AWS D11. D11 is the code for welding structural steel. That is what is used for civil construction. So to some extent, very different than ASME 9. To some other extent, more or less the same thing. This is a music sheet. In this case, what I'm showing you is essentially the blank staff lines, and says, okay, what type of groove, what angle, what root opening, how big the root face, all these things that we discussed during our terminology lecture, right? And that's why at the very beginning of the class, we do this thing that is so, I don't know, I don't find it particularly pleasant. That is learning this new language and learning all these new words. And even if we didn't understand exactly what those words were, now they're starting to come together as we discuss different things. But in these two previous slides, all I wanted to show you is what this music sheet looks like in welding, how we tell the welder, hey, this is how many amps, so many volts, and you have to prepare the weld, the groove this way. We talked about the variables, right? The welding parameters. And without getting into depth, because we're gonna see this in a little bit more depth later, but as you can imagine, some things should not be changed, and some other things maybe don't really matter, right? For example, if I change the alloy of my filler metal, probably that matters a lot. For example, if I change the gas flow by a little amount, in MIG, right? Or if I change the electrode diameter, but not by much, maybe it doesn't matter, right? And who decides that? Well, because we understand the fundamentals, we're gonna have a sense of why things can be so important or so not important. But when they are trying to make weld recipes for everybody, they say, okay, look, you don't think, we'll think for you. And this is what our infinite wisdom says. And in the case of ASME 9, it says, there are three types of variables. They called essential, supplementary essential, and non-essential. Obviously, the non-essential, they say, if you change it, is not big deal. The essential, and by the way, I'm talking loosely, I'm not an expert on ASME 9, and I believe we might have some experts in the class, so don't shoot me down yet. This is, learning the codes is like memorizing the Bible. But I just want you to give you a gist of, as we talk about a procedure, some things don't matter so much, some other things, like for example, the P number or F number, which means the alloy of the base metal or the alloy of the electrode, right? You cannot change just because you want. If you change that, you need to requalify the process, the procedure. And then there is this supplementary essential, that means if toughness is not essential, okay, let's not worry about those, but if we need to measure toughness, do a Sharpie test, then these other variables also matter, right? The supplementary essential. I don't want to get into the deep details of these, which are deep, and the ASME 9, to which you do have access to the latest version through the U of A library for free. And by the way, this is many thousands of dollars of documentation. You can, it's so deep, and you have specialists and special courses. But when it comes to welding, it says, all right, this matters and not so much. I mentioned ASME 9 a few times, but in case you wonder what the hell is this, ASME is the American Society of Mechanical Engineers. And one of the things that generated, that triggered the formation of this society is that boilers and pressure vessels were exploding, and they were having terrible accidents. And they got together to see what they could do to prevent this from exploding. And they wrote what is called the Boiler and Pressure Vessel Code, that is very old and has been evolving with nearly 100 years now. And by now, it's divided in many parts, from how you design a pressure vessel to how you weld a pressure vessel. As mean, the section 9 of this pressure vessel code is the one that says how you weld things or how you qualify things. And this determination of what's essential and what is non-essential comes from the section 9 of this ASME code. Okay, so that said, right? And if you want to make a pressure vessel out of titanium, ASME will say how you go about it. But for the vast majority of cases, we're going to be welding carbon manganese steel, low carbon steel. The vast majority of cases, so much so that some people say I don't even care about other things. I don't approve of that. I think rockets are not made out of steel, or seldom, and matter a lot. And you need to weld something. It's typically going to be structural steel. And you say, what I weld today, I'm going to do exactly what I did yesterday. And you know what? It typically works. It typically works great. So for all of you taking this class, let me tell you something. 90% of welds, you didn't need me. You actually don't even need to know how to read and write. You just do today the same you did yesterday, and almost always is going to work. And again, the problem is not the almost always, is that when things don't, who's going to help you? And that's the difference between first world and third world. And I know very well about one of those, right? Is you wanted to make a special pressure vessel for whatever reason you need it. For example, because you're dealing with oil sands. Chances are that what you did yesterday with the standard carbon steel might not help you. What do you do then? We need to know. All right. What can help you? All right, let's say I don't, what I did yesterday is not quite right for today. I'm gonna look at the supplier info. For example, this is information for 7018 from Hobart. And it says, well, if you get our electrode that qualifies for 7018 AWS classification, if you get the 1/8 diameter, you should run it between 90 amps and 130 amps and 165 amps. 130 is the sweet spot, right? And you would at 100 at the sweet spot, you should have more or less these volts, and it would be melt this amount of wire, and this is the deposition efficiency. We'll this have a whole lecture on efficiency, so let's not worry about this number right now. Fantastic. So either I do what I knew yesterday, from yesterday, and I'm good, almost always. I call my supplier, or I go to the website and download the specs, and already tells me the volts and amps. I'm styling. But let's say for whatever reason, you still need to do something that is a little bit more difficult. Then what do? You go to our Bible, right? Here I have it. I have two versions. Which one? This is, so, oh, the one I have here is the one that I got when I started my PhD. So now, if you have this book, oh my gosh, like if you have skimmed through the book, and that's why I said this book we need to have, especially for this lecture and for the next exam, you're gonna see lots of pages that look like what I'm showing you here, and I have some scanning the slides, right? AWS also has standards for some particular welds. So for some things in concrete, AWS also will tell you, this is the way you weld it. And these are expensive documents because somebody had done these welds and test them to make sure they work. And if you go to the AWS site, these are the B2.1 standards. And there's a whole family of standards, whether you're welding pipe or things for naval applications, sheet metal or plate, and different processes, MIG or stick or TIG, they have TIG here, and depending what base metal, right? So you have resources out there. Either you do what you did yesterday because it worked, you use the manufacturer's, the supplier of welding consumables. You use the Lincoln Procedure Handbook, which is an amazing resource. You can buy the AWS standards, the standard welding procedure specifications that I'm listing here. And even, there are even welding calculators. So I have these two myself, right? These are like slide rules made out of cardboard, but they are so useful. And you can go online, and pretty much every supplier of welding consumables or welding equipment right today has an app that says what thickness you want to weld, what procedure, what process you want to use. Will give you the volts and the amps and the travel speed. Why are you taking this class then? Right? Most of the time you didn't need this class, but you take this class because you will be the person who makes a difference when everybody else doesn't know what to do. You will be the person that when there is a problem can think, say, I think this is what's going on. I think this is what we can do to solve it. You don't need to take this class to weld what everybody else welds. But because you take this class, you will be able to do what few, if any, can do. And that's the point, right? But I want you to be aware of all these tools we have, because before we start thinking deep, we should use whatever is readily available. We don't want to reinvent the wheel. What could be those problematic cases that get people stumped? Things that have an off composition. For example, when you buy a steel, you say, I want a steel that meets these specifications. Sometimes they don't meet the specifications, and you need to have to authorize a deviation, or maybe you don't want to authorize a deviation, but somebody needs to deal with that. That somebody is paid well. Sometimes the plate material you bought says you should have all these things and you should not have all these other things, but they don't list all the periodic table. They list the things that historically have been relevant. It has been the case recently that some steels came with too much boron, but the standards said nothing about boron because boron was never a problem. And if you have some amount of boron, the hardenability of the steel is enormous. So you were buying a steel that met the specs as it was meant to be, but the steel sucked. It's even worse, you know what? From what I heard, in Europe, there are restrictions on boron in the steels. In North America, not. So the suppliers were sending the good steels to Europe, and we were getting all the other steels. Isn't that crazy? We need to understand what's going on so we can get good standards, and maybe we can have a client spec when we buy something, which now we do. Sometimes there are new alloys. For example, in the automotive industry, you have what is called the advanced high-strength steels that are incredibly strong steels, very difficult to weld. In the pipeline world, there's a debate about if going to higher strength pipeline material is going to be for the better, right? Because if it is stronger, can have narrower wall, and therefore is cheaper and is welded faster. So it's a cheaper pipe that gets laid out faster for lower money. On the other hand, when things get corroded, they don't care about the strength, they just corrode. And if you have a thin wall pipe, even if the strength is the same as a thick wall pipe, the corrosion resistance not very much. So high strength pipe, line pipe material used to be 65 KSI. Now people are talking about X100 KSI, which is called the X100. But whether it's good or not, I don't know. But it would, if we choose to do it, we need to weld it. Very difficult to weld a material of that high strength, right? How about materials with high alloys? How about stainless steels? How about non-ferrous? How about during the space race when people were trying to weld zirconium pressure vessels? What do you do? I mean, for sure, whatever you welded yesterday is not of much information to how to weld a zirconium pressure vessel. You guys are gonna do amazing on that. Sometimes you have problem cases like the client changes the specs. For example, this is something which my lab and I were involved directly. You make weld overlays that protect the base steel from wear. And everybody was happy with that. For some reason, which nobody knows why, nobody understands why, and I have suspicions that the reason was not too good, somebody decided to change the client spec. And now this material that was working very well, all of a sudden when people said, well, your overlay should penetrate up to this depth and have some properties, it was difficult to meet. And to meet those client specs, which in my mind were unnecessary, all of a sudden, we could meet all the other good properties we had before. What do you do then? Big problem that took years to figure out. Of course, it was figured out. But we needed to think beyond what we did yesterday and beyond what the supplier told us, because we were things that nobody had done before. Anyway, I hope I'm making the case that although most of the time you don't need all this knowledge, the few times that you need it is so difficult to find that these people are very valuable. And these people are you and I. This line of argument is not all that different than the firefighters. You don't use the firefighters all the time. And by the way, you don't want to use the firefighters all the time. But I would not want to live in a city without firefighters. That's what we are. When things go wrong and you don't have us, lots of time and money spent in trial and error. Most welding problems, the easy ones, have a problem, you weld again. And if you still have a problem, you change it here and there until you figure it out. When things are a big deal, that's too much money, too much time. So what we're doing today is I would like to navigate the Lincoln Procedure Handbook. So it's early in the course, and we're already going to do essentially what is the bottom line, like determine a procedure. And with that alone, you're going to be amazing when you get a job. And the rest of the course will be understanding this to see how it takes us to the next level. Okay, so let's see. So if you look at the chat, we have comments from somebody with Eddie has a long experience welding for real. And so if Eddie agrees with me, then it's definitely is true. So thank you, Eddie, for the comment. I'm going to start talking about steels. And of course, we're going to be able to do aluminum and zirconium. But steels is what everybody uses, what most people are using, and for which we have a lot of information. So let's not start running, but let's start walking. Okay. For a welding procedure, I want to plant this is a seed. We're not going to use this right now. But for designing a welding procedure, that is what we're going to do in the rest of the course, we need to do three things. One is we need to understand how the material responds to temperature. That is metallurgy. And we'll be talking about metallurgy starting on Tuesday next week. Second, you need to know what temperature you're putting in the material. You know how the material responds to temperature, but you don't know what temperature you're putting in. And for that, we need to do heat transfer. And I know many of you took heat transfer with me during the winter. You're gonna see what amazing things can come out from heat transfer, which we don't teach in the class, but it's very much similar to the things we did in class, and we can predict important things. And third, we need to understand the behavior of the process. Even if I have the same, for the same material with the same temperature experiences, it's not the same short circuit than globular transfer than spray transfer, because the physics, the mechanisms at play are changing the depth and the width of the bead and many other things that make the final look and the final properties of the weld. And we're going to discuss those when we talk about metal transfer and the plasma arc and other things. So, well, I don't need to say more about this book. And on this note, what I'd like to check with you, to go into a group task. So we are more or less 20 people in right now in the class, and what I'd like to divide you in groups. So you discuss things, and I'm gonna be popping into the different breakout rooms. I know of one of our friends here who doesn't have the handbook yet, so I'm going to make sure I pair this student with others who have the book. Does anybody else doesn't have the book? I think most of us do. No book. Okay, we have two. Anybody? Okay, thank you, thank you. You have to tell me. Okay. So we have 1, 2, 3. Okay. So what I'm going to do is give you a task. And the task will be using this book that most of you have, but not all of you, right? I'm going to split it in groups. And so it's about, I'm gonna make about like 6 groups, probably. And your task for all the groups will be to use this book to suggest a procedure for butt joint of 3/8 structural steel in the flat position. Please write it down, or actually, I'm gonna put it here in the chat. Okay, so this is what you need to do. I'll try to divide it in groups, so I'm gonna need a couple minutes in which I'm gonna get myself out, but in 2 minutes, please come back to the group, and I'm going to give you 20 minutes to discuss this with each other. And during those 20 minutes, I'll be popping into different rooms. What I'm gonna suggest is when I divide you in groups, you use your video, you get to know your classmates that you would have met in person in class, but now you're gonna meet virtually. You introduce yourself, your name, what your major is, maybe something interesting about your background. Some of us might be saying, my major is materials, but I have 10 or 15 years of welding already on my back. That's cool. And you try together to find a procedure, and then discuss what are the pros, what are the cons of this procedure, what other questions we might need to ask. You'll see some procedures have advantages and disadvantages, and until people give you more information, you don't know which one to choose. what would you expect about this procedure? So if we don't have any other question right now, what I'm going to do is try to use for the first time ever the breakout room feature in Zoom. No questions? Okay. So please stay with me. In about 3 minutes, everybody would be assigned to a group. All right. I think we're all back in the classroom now. If anybody wants to share with say anything in the chat, I visited each of you, and I think it went more or less okay. I hope you did. You guys enjoy it? Anybody wants to comment? Was it okay?
Yeah, it was good.
All right.
It was good to see some faces.
Yes. Isn't that that something new? Huh? Getting to see your other classmates. So we have 20 minutes, and these 20 minutes, what I would like to hear is what procedure each of us has done. So I would pick randomly somebody from each group to say a couple words and discuss that procedure. Let's start with Eddie. Do you want to discuss, Eddie, briefly what procedure you chose? You can say the page number.
Yeah, briefly, page 6.4-23.
6.4-23. 23. All right. Let's see. 6.4- oh, very early. Okay. 6.4-23. Hold on. Oh, we have a different version.
Oh.
6.4. Oh, no. Okay, no. We don't have a different version. It's that's what procedure is 6.
Yeah.
Self-shielded flux core.
You're close. Yeah, close. Mine is self-shielded flux core arc welding, semi-automatic self-shielded. Only thing to add that's not really stated in the question was the steel backing. We chose this because it's self-shielded. It's for structural. So for structural, this is commonly used. It's quick, and yeah, I don't know what else.
Hold on. I got it there, right? This is it.
Yeah, that's it. Yeah, for sure.
Yes.
It's
awesome
for 3/8 steel, and it has good, easy to work with, and especially if you have steel backing, you can really pour it on there, and it should be quick, right?
Yeah, and this is awesome. So something I find interesting in this, right? This has a steel backing. Sometimes we don't want to have a steel backing because it can be corrosion on the other side or something like that. But I didn't tell you that. So it was all open. But these are the type of things, that go to higher levels of thinking.
I think one good thing to note, though, is that for the backing, it's very common to use ceramic backing now, and you can just chip it off.
Right.
So although this does say steel backing, but it's something good to note, right? Because it definitely can get you out of a sticky spot sometimes, right?
This is awesome. And what I want to highlight here is, although you guys are only starting to take this welding class, as of today, you can go to a welder and say, look, for this particular application, if you weld it using this procedure, it's likely it's going to pass the qualification. This is very powerful. This class is not only about the theory, of which you'll see plenty, but you already have a magic trick in your sleeve when you have a job. So thank you, Eddie, for this the suggestion, and thank you to the teammates. So I'd like to move to another group. How about Aliza? Do you want to take over and tell us what your choice was, which cannot be the same?
Yeah, we chose the first one that came to us, which was the submerged or shielded metal arc welding. And it was the arc speed of 135 and current of 5.5 to 6.
So what page is that?
I just switched the number? Sorry. The current is
No, the page
135.
page number.
Oh, I'm sorry. It was supposed to be 6.3, page 5,
6.3.
or 6.2.
6.3.
6.225.
6.225. All right. 6.225. I'm looking it up because chances are that I already looked at it early in the morning. Aha, I like that.
Yeah.
Actually, this one I went deeper into detail. 6.125. So it's shielded metal stick welding.
Yeah. And we chose the one without the metal backing just because we didn't have enough instructions, and we thought that it would be better to go without it just because it's not always available.
Right. You see, a funny thing is when we come from an engineering side, we don't like the backing. It looks ugly. When you come from the welder side, you say, this is going to help me. And we go back to the fit for purpose. If it is fit for purpose, doesn't matter if it is ugly, right? So this is great. So here we have 3 passes in this one. And what is interesting about this one is the first pass is in 6011, right? If you remember, that's a cellulosic that has a potassium binder, so it can run on AC, right? Is what we would use with cheap welding machines. And 6027 is an alloy that an electrode that has lots of iron powders, so it gives you a very fast fill. Right, is similar to 6024, but it gives you a higher quality deposit. I don't know exactly why that is, but it is the alternative to a high deposition electrode when you want a slightly higher quality. Thank you. So yeah, this would be good. You realize, like Eddie just before was picking a flux core one. You're talking about stick welding. Both do the job, right? Now you have to see what you have in your shop. All right, let's move on to another group. How about Skylar? Do you want to tell us about your group choices?
Sure, we've found a couple. So one of the ones we were looking at though was I believe 6.3-67.
6.327. All right, you're talking about subarc welding. I like that. We're talking about all kind of processes, huh? Okay.
Yeah. So it was good for 3/8-inch commercial steel.
Is 37 you said?
67.
6.367. Okay, give me a second because I'm gonna show it to the whole class. I might have it subarc welding. The 367. No, I passed it. It's moving. No. I think it's no, not this one. Not this one. Show the middle. Subarc welding. Let's see. I need to recognize it. 316 to 38. Not yet. 38. Did you get it? Is it?
Yeah, I think.
Awesome. All right. So tell us more about this choice of procedure.
Well, we were just we looked at a bunch of different procedures, and then we chose this one mostly, I believe it was for the total time required. It was the shortest of all the ones that we found.
Yeah, that's awesome. And you know what? Of course, that's the idea of subarc welding, right? This high productivity. And if you remember our very first class, when I talked about the T-34 tank that the Russians were making, the difference between the Russians and the Panzer tanks is that the Russians were welding the tanks with subarc welding, and the Germans were using stick welding. You cannot compare it. So I like your choice too. Again, a shop might or might not have a subarc welding machine, right? So sometimes the decision is not as easy as saying this is just faster or this or that, but what do I have around? This is great. This is great. So let's move on. Wesley, do you want to tell us about what your group chose?
Yeah, absolutely. We did discuss a couple of them. However, there is a procedure on 6.3-44.
44?
6.3-44, yeah?
Yes. Okay.
I personally find this procedure interesting because it involves two different processes, SMAW and submerged arc. Plus it has the twin wire submerged arc, which is pretty awesome. 1,000 amps when we're doing the cap and stuff like that. But the initial closure pass would be done with SMAW, and then that side would be filled with twin wire subarc at 1,000 amps, and then flip it over, grind it, and weld the other side with subarc welding at 1,000 amps. It'll be fast, it'll be high quality. It is welded from both sides, but they're both in the flat position.
Yeah. So very interesting. So here we have one interesting thing to discuss. That is, in this well, we needed access from both sides. Other solutions had access from only one side. And sometimes we don't get to choose, right? Sometimes we cannot flip the part. So
absolutely. I agree. One of the things that I did mention to our group was that the constraints we had, it being 3/8 plate in the flat position, I said, there's a lot of other questions which will determine what we need to do. Do we have access to the other side? Just like you mentioned, what's the purpose of the weld? If it's only a seal weld, we could just, we don't even need to prep the joint at all, just weld over the, where the two plates meet. But this procedure is totally overboard. So that's what I found. That's what I thought was interesting.
Yes. About this procedure, typically these stick welds are just seal welds, so you don't like drip metal to the bottom from the subarc at that massive current. But what I wonder, and I don't know, but what catches my attention is we have the highest possible productivity in the subarc welding, but preparing that stick weld seal is gonna take forever. Sounds kind of contradictory to me. Sounds like it's gonna take longer to prepare the backing weld than to weld.
Yeah, I agree. This would be often encountered in the vessel fabrication. For instance, doing all the welding is done in a flat position, but you're rolling the workpiece.
Mm-hmm.
And it would often, you would use a GMAW first pass, MIG route, you would call it. But the first pass needs to have enough, needs to hold enough heat so that when you are welding with the sub arc, it doesn't start cutting through the weld, in which case it'll cut anything in its path. As soon as you start busting through with a sub arc, it just cuts it like a torch. So yeah, I've seen that, I've done it, but yeah, this procedure I found interesting. So
yeah, I think it is. I think it's awesome. Also, it's a twin electrode, right? It's a single welding machine that is running 2 wires.
right, or it could be 2 power sources hooked up to the one sub arc machine. This was something we did at Dacro, doing the diesel desulfurization vessels for Esso. They were 9 inches thick with a groove that was 1 inch wide, and you're running twin wire that was all the way down in this groove. And it was, yeah, it involved a lot of training, a lot of QC and all that stuff. But yeah, twin wire, pretty crazy.
This is awesome. And as we switch to, I would like to call Jolene, I remind you, like the amazing thing here, that I gave you such a clear statement, say, weld these 2 plates of this steel at this current, at these 2 plates of this thickness in this position. And there's so many ways you can do it. So far, we have 4 different solutions that involve 4 different processes. 2 of those are sub-arc welding, but one was with 1 electrode and the other is with twin electrodes. Very interesting. So Jolene, because you were the last, you must be like, I hope you had something that nobody mentioned before.
I hope so too. I've kind of lost track of the numbers, to be honest, but one I think that we haven't done is 6.7-7.
Whoa, okay. So that's 677. That's big. And this is awesome because I also saw it. So let me go there. I scanned 31 solutions today, although some of those were for other positions. This is what you said, Jolene, right?
I believe so, yeah.
All right. So what do you see in this weld?
Well, it's a little bit unconventional because it's TIG welding, which is a highly, manual, intense, like slow process.
Mm-hmm.
And it's also, I think, not really something that you would do, I don't think, for like a structural member, but anyways, I guess that anything's possible in this scenario. So yeah, you could do a 1 pass on the butt joint there and just basically fill it up.
And well, in this case, we would have 5 passes.
Oh, you would go all the way to 5 passes.
Well, you don't get to choose. The way we read this, and let me get.
Okay. Oh, that's for the first pass. And
first pass and a second, third to 5th pass. So funny enough, right? We have procedures that was like 1 massive weld, and now we're thinking about 5 kind of surgical welds. I could imagine this could be used for some like very difficult application in pressure vessels. I don't know if any of the welders here have a better thought, but doing this with TIG sounds like cutting a tree using a scalpel.
I mean, painful.
Yeah.
Yeah, but thank you for suggesting that one, because as we got to see, for the same weld, we can do it in 6 different ways that are very, very different. And there are pros and cons to each of those. And if all you know is what you did yesterday, it's kind of all the same to you. But through this class, what we're going to be discussing, for example, is what are the heat input implications of having chosen these different procedures. So this is perfect timing to stop here, but I hope you enjoyed the exercise, and I hope you feel the power of right today being able to go to a welding shop and say, I think these conditions would give us a reasonable weld, and chances are you would be right. It's awesome. So Thanks, everybody. Thank you. And I'll see you on Tuesday.
Thank you.
Yeah.